Okay, so I left you with this little sum to work out how long it would take the Andromeda Galaxy to collide with the Milky Way when it's approaching at 300 kilometers per second and has 0.9 megaparsecs to travel. So that's just a straight B over V calculation, a bit like we've done before. And if you work that out in years, you end up with 3 billion years. Okay. So by that reckoning, then, you know, the M31 will have collided with the Milky Way even before the end of our sun's main sequence lifetime. But like I said, then it probably wouldn't actually affect the solar system too much, as nothing would probably disturb us. The night sky will look a bit crazy for a very long time. But yeah, it's probably not terminal. There's been some, obviously we were assuming that both galaxies were heading directly towards each other, and that isn't usually the way galaxies interact. And so more recent work, actually again by the Gaia satellite, has worked out the proper motions of stars even in M31. Excuse me. So that we can work out, in a sense, the true trajectory of M31 relative to us. There's also another nearby galaxy, M33, in here as well, but you can see the trajectories. They'll come, us and Andromeda will come in and do a little orbit around each other and then head in for the final merger. So no doubt we will eventually become some sort of joint elliptical galaxy as well. There's a very nice simulation if you go to this website, so I'd urge you to do that. So again, very similar to the one I showed in the workshop 4. So please have a look at that one as well. So to show the movies of the sort of simulations of what happens when these two spiral galaxies collide and basically turn into an elliptical. Okay, so now let's change topics slightly and talk about active galaxies, which is a initially, it feels like we're talking about a sort of small subset of all galaxies, but towards the end, we realize that this is actually much more general and applicable to all galaxies in principle. But there is a class of galaxies that we see today that we refer to as active galaxies. And these have something interesting, very interesting, going on in their very central region. So in what we will refer to as the nucleus of the galaxy. Okay, so these active galaxies have a very luminous point of light right in the middle of the galaxy. And so these are often referred to as active galactic nuclei, or AGN for short. So AGN is a big branch, sub-branch of astrophysics. And they come in all shapes and sizes. Again, you can read about this subject in the textbooks. I don't want to get too hung up on the kind of zoology of it all. There's quite a lot of different subtypes of AGN. I'll mention a few in passing here, but that's not really the core of this module. It's more to do with understanding the basic sort of idea and physics behind what are powering these strange nuclei. So there are some, so there's a vast range of luminosities of these point-like sources of light in the middle of galaxies. And the most luminous ones, basically all you can see, certainly in most bands, is the nucleus itself. You can't even see this galaxy there. So that's quite a strange sort of thing to go on. I'll show you some pictures in a moment. Things get more weird when you try and examine the light coming out of the very center of these galaxies. It doesn't look like anything like normal starlight at all. So there's no sort of black body continuum. Instead, there is a so-called non-thermal continuum, which usually is a sort of power law type spectrum that increases towards higher energies. So pointing towards quite high energy phenomena going on. And instead of absorption lines like you see in a normal spectral starlight, you see emission lines. So this is telling us that there's sort of extended hot gas there somewhere. that's being heated up. And again, I'll show you spectrum in a moment. But the emission lines that you see are extremely broad in terms of the width of the line profile. And the only way to explain such very broad line profiles is basically due to sort of bulk motion at high speed. So basically the Doppler effect again. So it's also telling us that the hot gas that's in the center of these galaxies is moving around at very high speed. So I'm going to sort of outline the various sort of observational properties that need to be explained, and then towards the end we will zero in on a model, well, more than a model, what actually explains all of this stuff. Okay, so let's have a look at some examples. So this is at the mild end of activity. So, you know, there's what looks like a fairly normal spiral galaxy here, okay? But the unusual thing is this point in the middle here, okay? So that's not a star like that, okay? This would be a foreground star in our own galaxy, or this, okay? You can see it is point-like, so it looks like basically looks a bit like a star, but it's right at the center of the galaxy, and it's definitely something in this galaxy and not a foreground object. So these type of galaxies, you might see in the textbooks, are referred to as Seyfert galaxies, named after the astronomer who first sort of identified and catalogued these. So there's quite a lot of examples of these. So these are relatively nearby, and like I said, at the low end of the activity that you get in the centers of galaxies. So this is a sort of a low luminosity version of the phenomena that we're talking about. Okay. So just a slightly brighter nucleus than you normally get. But then you go to the other end of the scale, as it were, in terms of the luminosity of this activity, and you come to objects that are referred to as quasars. So quasar stands for quasi-stellar object, and that's because when they were first discovered, again, they literally just look like stars. Okay, so this is a quasar, okay, in an optical image, okay, and it doesn't look any different to all of these other objects, which are just foreground stars. So what was different about this object, and is given away by the name here, this is the third Cambridge catalogue of radio objects. So the Martin Rao telescope at Cambridge where they invented radio interferometry, did a lot of these early surveys looking for new radio sources all over the sky. And once you found a strong radio source, you'd go and see what was there in the optical, and this is what they see. Okay? So it just looked like a normal star. So the next thing to do was to try and go and get a spectrum of this object to find out why it was emitting such strong radio waves. And they found out that it wasn't a star at all. It was one of these active galaxy nuclei type spectra, emission lines, and usually quite high redshift objects. So we'll see this in the coming lecture, which, as we shall see, means that these objects are very, very far away. So these are galaxies that are a long way away, but you can't see a galaxy here. All you can see is the blinding light from the center region of this galaxy. It's very hard to see the galaxy in these objects because you're so blinded by the amount of light coming out of the nucleus. So here's an example of a spectrum. This is like one of these Seyfert galaxies that I just talked about. So if you take a spectrum of just the point of light coming out of the middle of the galaxy, this is what it looks like. So as you can see, there are emission lines here. So some of these look familiar if you go back and look at like the spectrum of the H2 region that I showed you a few lectures back. You get similar sort of lines here. But what's different this is the H beta line here, so one of the DARA lines, and H alpha would look the same, is the fact that you've got this incredibly broad line here. So you've got a little narrow bit on the top, but the rest of it is really, really broad. Okay. Again, excuse the wavelength scale, which is in angstroms rather than nanometers, but you know, this 10 angstroms in a nanometer, so this is 500 nanometers roughly. Okay, but you know, you can look at this and measure the width of this line, sort of from here to here, compared to the line center, which is here. and work out what kind of velocities gas would have to be moving at to fill out this very broad line width. And it's thousands of kilometers a second. So this stuff is moving around very quickly. So these broad lines are very characteristic of active galactic nuclei. And just returning to the quasars for a moment. So yeah, another discovery enabled by the high spatial resolution of the Hubble Space Telescope was to actually be able to find the host galaxies for these quasars. So here we see an example. Okay, so you've still got the very bright point of light in here, but because Hubble could focus that into a very small region, it then reveals the galaxy that hosts this very bright nucleus. So you can see here, looks like some kind of spiral galaxy, perhaps. Similarly here, I can't really see what's going on here, but these look very reminiscent of tidal tails. And again here, and this one's got a nearby companion as well. So this was what was found when Hubble started looking at these quasars, is that they all seem to be in some interacting and merging in some way or another. So that is another clue to perhaps what's causing this kind of activity in galaxies. There seems to be some link with interaction. Okay. So another key part of the puzzle in trying to understand what's going on in the nuclei of these galaxies is to try and get some sort of handle on the size. Now, as I was saying, the light seems to be coming from a point, effectively, on the images. And it's difficult to resolve. Well, no one's ever really directly resolved that emission very well until recently, which we'll come to at the end. But you can get a handle on the size of an object by another method using time variability. Okay. So most active galactic nuclei are highly variable. Their brightness, the magnitude of that central point of light, varies on timescales of months, very typically, sometimes even weeks or even days. Okay, so the brightness will be going up and down fairly randomly on those kind of timescales. So it's a sort of a common physical concept used, certainly in astrophysics, is that the timescale of variability allows you to place an upper limit on the size of the region that is doing the emission. Okay, and this all comes from a light travel time argument. So if L is the upper limit on the size of your object, it's given by the speed of light times the variability time scale. Okay, so here, if an object is varying on the time scale of 1 month, then the region can be no bigger than, well, for want of a better unit, 1 light month, how far light would travel in a month, okay, which is about the size of the solar system. Okay, so 100 AU, something like that. Okay, so let me just sort of put a bit of physics on this, but this is the key point anyway. If something's varying significantly, and by significantly we mean, not just by a few percent, but something like a factor of 2 or something. So if something doubles in brightness, that's a significant variation. And how fast does it change gives you a limit on the size of the region that is emitting that light. And this works at any wavelength. So here's a little diagram to try and explain some of the physics behind that. It's just a sort of a hand-wavy explanation. But imagine you've got a cloud of gas that's emitting, say, those emission lines, for instance, in the center of the galaxy, but the continuum light pretty much does the same thing. Now, this is all to do with kind of the concept of causality as well, okay, and light travel time. So in order for something this big to vary significantly, let's say it's going to brighten by a factor of 2, And let's assume that the increase in brightness is due to an increase in the temperature of the gas, okay, which is one way to increase the brightness. Okay, might not be the only way to do it, but let's assume that for a moment because it's one of the easier ones to sort of understand. So imagine that, say, you heated up this end of this subregion in the cloud by increasing the temperature. Okay, it would be, the whole cloud would not vary, increase in brightness if, some bits were randomly increasing in temperature while other bits were randomly cooling in temperature. It would then all end up, at the same sort of brightness. It wouldn't be coherent. So that is another key word here. You need whatever change is going to increase the brightness of your emitting region, you need that change to be coherent throughout the cloud. So the way that information travels from one side of a cloud to the other could be, for instance, that you heat up this bit and then the radiation from here penetrates through the rest of the cloud and heats up all the rest of the gas on the other side. So what is the fastest speed at which that sort of information that we're going to be increasing in temperature can propagate throughout the cloud? The fastest that could ever go is the speed of light. Okay? And obviously, with kind of radiative heating, then that radiation would travel at the speed of light, although it would probably still take much longer because it would be interacting as it goes. But that's the idea of that. There's an upper limit on these on the size of an object given by c times t, where t is the variability timescale in this case. Okay, so if something is varying on the timescale of a month, it can't be any bigger than 1 light month. Okay, so that's telling us that whatever the hot emitting region in the middle of these galaxies is also very small. Okay, so 100 AU, the size of our solar system, and all that luminosity is coming out of there. Okay. So here's a typical light curve of, this is just the continuum light here, for an example of an active galaxy, just the nucleus. So here's the magnitude, okay, and this is varying over many years here. So it kind of flares randomly, okay, so every now and again it gets quite a bit brighter, okay. So it goes from 17th magnitude up to 12th magnitude, so that's a difference of 5 magnitudes, which corresponds to a factor of, I can hear you all answering, good, 100, okay, so a difference of 5 magnitudes is a factor of 100. So these objects are changing in brightness by a factor of 100 here during these sort of flaring events, okay. But even the rest of the time, they're going up and down by factors of 3 or 4 here. Okay. And you can see the sort of fastest time scale that it's changing here, is certainly on the order of months. Okay. So the faster these things vary, the smaller the emitting region must be. So this is now the puzzle. How do we get so much energy out of a very small volume of space, okay, and also explain all the other phenomena as well, the non-thermal emission, the fast motion, etc., etc. Well, people puzzled over this for decades, and everybody has come to the conclusion that the only way to explain this incredible amount of energy coming out of a small region, because if you, again, if you look at the amount of light there in that nucleus, certainly for the quasars, it's more energy coming out of there than it is the entire galaxy. So this is rather reminiscent of supernovae explosions, and for a long time, people tried to explain the phenomena in the center of galaxies as being due to a succession of supernovae explosions. It would explain the variability, it would explain the kind of emission lines, etc., etc. But the most extreme examples are so extreme that you just could never get enough supernova going off at the same time in such a small volume. You can't pack hundreds of stars into something the size of a solar system and let them all explode. If you do try and pack that much material into a very small volume, you know where you're going to end up. Okay, you're going to end up with a black hole. So we are back looking at black holes here. but these are different, okay? And what's different about them is the superlative on the beginning here. These are supermassive black holes, okay? And that's the only way to explain this amount of energy, and we'll go through that calculation. In fact, you can go through it yourself. So, so this idea of getting a high luminosity out of a small volume, and the small volume comes from the light travel time. The high luminosity is what you measure, you know, from these points of light at extremely long distances away. Okay, the only way to produce that amount of energy is the release of gravitational potential energy falling onto a very massive compact object, and we mean very massive. Okay, we'll talk about that in a moment. So this leads us to the idea of supermassive black holes. So before we talked about black holes, you know, at the end of being left behind when a single massive star explodes in our galaxy or anywhere. So that would give you, you know, a 5 or 10 solar mass black hole perhaps. But here we're talking a lot more than that, as we shall see. Okay, so the luminosity of these objects, so that these, certainly the quasars, are the most luminous objects anywhere in the universe. Okay, so let's do a little back of the envelope calculation of how much energy you can extract with dropping mass onto a black hole. Okay, so let's just go back to basics. So gravitational potential energy, if you drop a mass little m onto some kind of spherical object that is mass m and radius r, then the amount of energy you get out is given by this equation. Okay, so that's extracting gravitational potential energy by dropping a mass m, little m, onto an object mass, big M. So now let's just introduce a bit of nomenclature. Let's keep doing that at a certain rate. Okay, so we're going to constantly allow mass to fall onto our compact object at a given rate. Okay, so that's referred to usually as a mass infall rate. Okay, and often given the symbol m dot, which is just shorthand for a time rate of change. So how much mass per unit time. Sorry, I'm dropping into calculus notation here, but just we're not going to do any calculus. So this is just an amount of mass, usually measured in solar masses per year, of gas basically falling onto the compact object. Okay, so let's now turn some fraction of that energy into radiation. Okay, so if we just go back for a moment, okay, all we're doing is looking at the time rate of change of both sides of this equation. So dE dt, if you like, is just power. So that's the rate at which energy is emitted per unit time. So that's just luminosity. And then on this side, this will be the time rate of change of the mass infall. So that's the m dot here. Okay, so that gives us this equation here. And I've introduced a little efficiency factor because not all of the energy, gravitational potential energy, is going to be turned into radiation. So by sort of observations and theory, then we think about 10% of that gravitational potential energy will end up coming out as radiation from very near the compact object. So you end up with this kind of formula. Okay, so this is the luminosity generated by dropping mass at a certain rate onto a compact object, mass m, size r, okay, with some kind of efficiency. Okay. Okay, so something we haven't looked at yet, although we kind of alluded to it before, is the idea of an effective size of a black hole. Okay, so this is the famous Schwarzschild radius, or event horizon is another term for it. Okay, and it's given by this equation. Okay, and you can look this up for yourself, really, or derive it for yourself. Obviously, this really requires loads of general relativity to derive it properly, but a classical Newtonian solution where you put the escape speed for a spherical object of mass m and radius r equal to the speed of light, and you come up with this equation. Okay, so again, if you want to prove that to yourself, just think about escape speed from the Earth, for instance. you know, how fast do you need to get a rocket moving before it will escape the gravitational pull of the Earth. So basically, you just equate the kinematic energy of the rocket to the gravitational potential energy at the surface of the Earth, and you will end up with an equation that looks like this. And then you just put the escape speed equal to c, and you end up with this equation. Okay? So that's what the event horizon really means. It's where gravity is so strong that even light itself cannot escape. And again, recall that light photons do have energy, and therefore they also have some equivalent mass and momentum. And so they have equivalent mass, therefore they are affected by gravity. Okay, well, let's use this now as an effective size for the black hole, because once it's gone inside the event horizon, we can't see anything anyway. But up until that point, the gas and any radiation will still be highly visible. And you know, that gas will be heating up as it gives up its gravitational potential energy. So gas gets hotter and hotter as it gets close to the event horizon. And hot gas is emitting like crazy. So you know, it's anything but black up until that point. So if you put those two equations together, if you take that size and put it into the previous equation, yep, this one, okay, so just put the Schwarzschild radius in there. You can see the mass is going to cancel out and g is going to cancel out. So you end up with quite a simple equation that the amount of energy from a radiating black hole now, okay, so from the material falling into it is, you know, some efficiency, which we've said is around 10%, times half m dot c squared. Okay, so this looks like an energy equation. Okay, so remember Einstein said E equals mc squared, and this is just the time rate of change of that. So luminosity is m dot c squared. Okay. So if you sort of look at the typical numbers here, okay, so we've said that epsilon is 0.1, if you like, 10%. And so this is half of that, so that's 5% of the rest mass energy is extracted. So mc squared would be what we would call the rest mass energy. So if you literally took the mass and turned it all into energy, that's how much you would get out of it. So this process of accreting onto black holes gives you 5% of the rest mass energy. So it's interesting at this point to compare this back to what we looked at the beginning of the course when we looked at nuclear fusion. Okay. So if you recall, the fusion of hydrogen into helium extracts 0.7% of the rest mass energy, if you like, out of the hydrogen. Okay. So this process of dropping material onto black holes gives us you know, over 10 times more energy than, or about 10 times more energy than nuclear fusion itself. So this is why we need this kind of process to explain these extreme luminosities. Okay. So the quasars, just the nucleus themselves, can be much, much brighter than an entire galaxy. So like much brighter, more luminosity than 10 to the 11 stars. So time for you to put something into practice. So if you just take this equation, the one I've just talked to you about, again, just make epsilon equal to 0.1. So estimate how many solar masses of material must fall onto a supermassive black hole per year in order to explain the most luminous objects in the universe. So the most luminous quasars that we know about have a luminosity of about 10 to the 13 solar luminosities. Okay. So that's what I'm talking about. So this is like probably 100 times more luminous than our entire galaxy, which has 100 billion stars in it. Okay, so that's, and you've got to get it all out of some extremely small volume in the center. Okay, so work out the infall rate. If you can work it out in solar masses per year, then that would give you a feel for what we're talking about here. Okay, so have a go at that, and we'll see you after the break.